Okay, so we're just got into chapter 4 and we're looking at applications of the derivatives, and we were looking at finding local maximum and minimum values and absolute max and min values. Another way that you might hear it be phrased is extreme or extrema. So finding the extrema, that's just plural. Extremum is plural for extrema. And those are just the maximum and the minimum values of a function. Okay. So in other courses in the past, you've had to use a calculator or a graphing calculator to calculate max and mins of a function. Right now, we're learning of tools of using calculus to find those extrema. And we're looking at how to distinguish between, is it an absolute or a relative, which is also meaning a local extrema. Okay. So you'll notice that when you're doing the homework and they're asking you what the absolute extrema is, or what is the local extrema, you're putting in the biggest or the smallest y value. Well, if it's the absolute, it's the biggest y value on the graph, and if it is the absolute minimum, it's the smallest y value on the graph. Okay, so by definition, so let f be defined on an interval that contains c. And f of c is the minimum of f on the interval. So let's just draw a graph real quick. And so let's say we have something like this. We have some c value here. And we know that f of c is our y value. It's telling us that on our interval, and so maybe we have it from A to B, that f of c has to be the smallest or equal to the smallest value of all the other y values for x in that interval. So that's kind of the formal definition of being a max or a minimum point. So same sort of idea if we're looking at a maximum point on some interval at a value of c. So we have some c value here, f of c, which is our y value when x equals c. Notice that this is the largest y value on that graph for some interval AB. And it doesn't matter where we put that AB, but in between, and it could be given to you. And that's the largest y value within this interval. Okay. So the minimum and maximum of a function on an interval are extreme values or extrema of the function on the interval. The minimum and maximum of a function on the interval are also called absolute minimum and absolute maximum, or the global minimum and global maximum on the interval. Extrema can occur at interior points or endpoints on the interval. So we were looking at that yesterday. We were looking at when is our derivative equal to 0, and those were our critical points. And we were also looking at what was happening at our endpoints. So a function may have both a maximum and a minimum value over an interval, only a maximum, only a minimum, or neither a maximum or a minimum over an interval. So let's try to look at these examples and determine why or why not it has a max or a min over the intervals given. And so if you look at this example here of this graph, and we're looking at find the absolute and extrema of the function over the given interval. Use the top graph. Okay, I copied and pasted. So right here, do a different color. We have the interval from -4 to the interval of 0. So it's a whole picture of this graph. And so if we look at in between here, there's a highest point right here, right? And so when x equals -2, f of negative 2 is equal to 2. And this is so this is, notice, highest value on the graph between -4 and 0. And so this would have to be an absolute.
Professor.
Yes?
You're going a little bit too fast. Did you want us just to jot down the graphs, or did you want us to jot down like all your notes before you do the graphs as well?
Right.
Because I mean, like, you have all this stuff written down, so we're trying to, I'm trying to copy them all, but then like you slide down a little bit too fast because of explaining it. So it's a little bit hard to catch up.
Yeah. So Jason, I don't know if you didn't catch it, but these notes right here I posted last night.
Okay.
On Canvas on the front page. I tried to put it in bold letters that you guys would see it, so that maybe you had it printed out beforehand, but you do have them and it's all typed out for you, so you technically really don't have to type out those pieces. All
right. So then for our notes, it's just the stuff we're just going to be copying off of the graph, correct?
Right. And we'll extend and I'll write in more on these where we might do more problems. But for now, what I would do is just copy the graph down if you don't have it in front of you, because they're all pretty much similar for at least the next few examples. They're all like that semicircle between -4 and 0. And then we'll discuss absolute max and absolute mins between those intervals.
All right.
And so notice that when x equals -2, we have an absolute max of 2. That is our y value, the biggest y value in between x equals -4 and 0 and including. If you look at the minimum value, I can see that those minimum values, there's 2 of them. They're occurring at x equals -4 and occurring at x equals 0. So x equals -4 and x equals 0. Notice that f of -4 is the same y value as f of 0, and that y value is 0. And so we have 2 absolute mins. And the absolute mins occur at 0. Okay, so that one was okay. Notice that those bounds on that interval were closed. So I was including -4 and 0. Where if we go to the next example, so same thing, but now we're looking at the interval between -2, x equals -2, including it, to 0, but not including 0. And so let's just look at that. So we're looking at -2, so we're including it. And we're going to 0, and we're not including it. And so if you look at just this piece in here, that's a solid circle here, to an open circle here, right? Because it's not including it. The largest value that we're getting, the largest y value we're getting is 2. And so again, I see that we have an absolute max. In this case, again, when x is -2, and the absolute max is +2. So what about a absolute min? So looking at this graph, can you give me an x value that gives me the smallest y value on this between -2 and 0, not including 0? So I can't say 0 gives me the smallest value because it's not included on my interval. And so, I mean, I could say, what about -0.01? That could give me a really small value. Or what about, and I can't see any chat if you guys are chatting. But you can always get closer and closer to, this is kind of our reasoning of limits. We can always get closer and closer to 0 on the left. We're approaching 0, but you can always give me a number that's less than 0 that's going to give me a smaller y value. So there's no absolute min here. Because x equals 0 is not part of the interval. So looking at the next example, -4 to -2. And so looking at -4, it's not including. And -2, it's not including. And so we have open circles there. And so is there any value that you can say x gives me this largest value on this graph? So I can choose some x value getting closer and closer to -2 on the left. And it's going to get like 1.9. When we could choose something closer, and it might give me 1.99, but I can choose something even closer to that, which give me 1.9999. So I know it's approaching -2, but there's no value that is actually giving me back -2. So in this case, there's no absolute max or absolute min. So endpoints of the interval are not included. Okay. If I was looking at limits though, those limits would exist and they would go to either 0 if I was approaching -4 on the right, or -2 on the left, I'm going to 2. But there's no absolute max or absolute min. Okay, so the next example, almost similar in the graph, except that you have an open circle at -2, and you have a point where it's defined when x is -2, y is 1. And so if we look at this and we look at our graph, it's saying it's including -4. So there is a solid circle there, and we're including 0, and there's a solid circle here. So I'm including my endpoints of my interval. And so what about a absolute max? Do you see an absolute max?
Is there no absolute max because it's open circle?
Right. So there's none. Again, same kind of reasoning there. It's not defined there. I could say if I was looking at the limit as x approaches -2 does exist. It's 2, but that point doesn't exist there. And so I can't take any interval surrounded by this and have all my values of x always smaller than or equal to it. But for an absolute min, so these are included here. So we do have a smallest y value. We have smallest y value of 0. So our absolute min is 0. And it occurs 2 places. When x equals -4 and when x equals 0. Okay, so from looking at this example, you should be able to tell what's needed. So there's two things that's needed to be the case for there to be both a maximum and minimum for the graph. So did you notice what had to be the case in order for a max and a min to occur?
It had to be like less, like it had to be brackets, not parentheses, and there couldn't
Okay.
be any open circles.
Right. So it had to, the interval that had to be on a closed interval. So our endpoints had to be included. And when you said it couldn't have an open circle, so basically it has to be continuous. There can't be any jumps on that interval that we're looking at. And so in order for there to be both a max and min, the interval we choose X to be contained in. Interval has to be closed. And the function needs to be continuous there. In the interval. So basically, this is a theorem, and this is what is called the extreme value theorem. So it says if f is continuous over a closed interval a, b, then f has both a minimum and maximum over that interval. Okay, and so basically we were doing this yesterday. So this is kind of just reviewing what we were doing yesterday and kind of putting things more together in words and theorems that you might see. And so relative extrema and critical points. So again, relative extrema, that's going to occur where you have at some value C, and FFC is going to be the minimum if it's the largest value, maximum, if it's the largest value for any y value or equal to in that interval. And it's going to be a minimum if f of c is the smallest y value in some interval. So basically, relative extrema exists when the value of the function is smaller or larger than all the other function values relatively close to that value. Okay, so looking at the following example, there's two of them. So locate the relative extrema in each of the graph and determine the value of the derivative. Okay, so relative extrema is just telling me to look at this, and I'm looking for all of my maximum and minimum values that occur. It hasn't given me any closed interval, so I'm just going to assume that these graphs are continuing at their end behaviors in the direction they're going. And so looking at this, I can tell that at this point 0, 0, what type of point is that? And I have a point here at 2, -4. And so I can sandwich that point 0, 0. I can choose any interval around that, small or big, and that's going to be the biggest point in that interval. So like if I just sandwiched it in here, right, this is the biggest point for all the y values where I had just chosen. And so by definition, then this is a maximum point. So at x equals 0, you have an absolute max of 0. And then looking at our min, right? We have an absolute min at x equals 2 of -4. So looking at that max and min, what can you tell me about the derivative when x is 0, and what can you tell me about the derivative when x is -4? So if I'm looking at the equation of my tangent line, if I'm following along this like a road, and I come to change direction from increasing to decreasing, right? It's going to become horizontal tangent line there, right? And then I'm going to change it. Then I'm decreasing and I'm coming, and then I get to my minimum value. But while I'm changing direction at that minimum value, my slope is 0. And so at this relative extrema, our slope is equal to 0. So f prime of c equals 0. So look at the other graph. So that looks like an absolute value function shifted over to the right one. So, but notice that does have an absolute minimum, right? So there is a place where the value is the smallest. And so we have an absolute min at x equals 1 of 0. I don't see any max because I'm assuming these are going on forever unless it closed an interval for me. So no absolute max. But what do we know about the derivative at x equals 1? So what happens when we were looking at derivatives of sharp corners? So this right here, the derivative, f prime of 1 in this case, does not exist. I could choose it looking at my tangent line. If I'm coming this way, it would be negative. But if I looked at my tangent line and I'm doing it this way, it's positive. It's not the same value. And so it just doesn't exist. So this is where I was saying to find critical numbers, you're looking at when your derivative is equal to 0. And you're looking at when the derivative is undefined. It has to be defined though, because that's part of being an absolute max or absolute min. It has to be defined in the original function. So if you find values that set the derivative equal to 0 or values where it's undefined for the derivative, those are called our critical numbers. Oops. Okay, let's jump around. Okay. Okay, so those are your critical numbers. Sorry about that. So relative extrema, so a max or a min are only going to occur at critical numbers unless you're looking at a closed interval. And it's going to occur when x equals c if it's a critical number. So if you look at this graph here, the graph of f of x is shown. Label f of a through f of c as either an absolute or relative extrema. So let's look at this one, and let's just look at, first of all, the highest value of your y value. And so where would that occur? And so I notice this is my highest y value. So I can see that at x equals c, f of c is an absolute. Extrema, which it is a max, is the type. If you look at f of a, so we were looking at the interval between a and c, right? I know it just says label it. So f of a, so when x equals a, f of a is a relative. Another way they call it is local max. Because it's not the highest one on that graph. And so looking at this at B, I notice I have a minimum value. But if I look at the smallest minimum value here, actually just says label f of a through f of c as absolute max or absolute min. So we don't have to look at this. So f of b, well, if I'm again, sorry, that's where I saw that before, f of a through f of c. So I don't have to look at these endpoints here. So this is going to be it's the smallest value on there, absolute min. And I'm just going to put the case that if x is only contained between the interval a and c. Okay, so remember before when we were looking at taking the derivative, we saw that the slope was not always just 0 when we had a maximum or a minimum value. And so that's important to remember. So just because the derivative is equal to 0 or undefined does not mean that there's a relative max or a relative minimum at that point. The sign of the derivative needs to change signs for a max or a min to exist at that point. So this does not occur at every critical point, but it only can happen at a critical point. Okay. So if it's going to have a maximum or minimum, that's telling me that the derivative either has to equal 0 or it has to be undefined. But if the derivative is equal 0 or undefined, doesn't actually mean it's a max or a min. But it has to be 0 or undefined to be max or a min. So here are your guidelines, and this is, I believe, what we were doing yesterday. So guidelines for finding your absolute or relative extrema on a closed interval. So you're going to find your critical values or numbers of f on your interval. Do this by setting the derivative equal to 0 and finding where it's undefined. These critical points and endpoints make up a list of candidates for the extrema. So then we got to evaluate each candidate by plugging these numbers into the original function. The least of these values from the previous step was our absolute min, and the greatest of the value was our absolute max. So critical values are always the x values, while the max and min values of our function are always your y values. So in other words, if you were looking at a point 270, the relative minimum, so the point 270 is a relative minimum. The minimum of the function is, so the minimum of the function is the y value 70, but it occurs at the x value, which is 2. Okay, so we're just going to follow what we were doing yesterday. And so we were looking at examples yesterday and doing this. So we were looking at finding when the derivative was equal to 0. So we need to find critical numbers. So we want to look at f prime of x. When this is equal to 0 and when f prime of x is undefined. And so taking the derivative, well, the derivative of 2x is just 2 minus 3, so derivative of x to the 2/3. So bringing down our power of 2/3, subtracting 1 from our power. So 2/3 minus 3/3 is negative 1/3. And we're looking at this at the interval from -1 to 3. So we want to look at when is this equal to 0. So I'm going to rewrite this a little bit when I'm setting this equal to 0. So I have 2 minus, well, notice my 3, those cancel. So I'm left with plus, or minus, sorry, minus 2 all over. So let's bring down x to the -1/3 power so it's a positive exponent. And I'm just going to rewrite it as a radical. And so this is really the cubed root of x. And we're looking at when is this equal to 0? Or undefined. We're looking at this, x can't be a value which sets the denominator equal to 0. So x can't be 0. I'm okay back in the original problem with x being 0, but for my derivative, x can't be 0. I notice that I can solve this equation on the left. I can clear my fraction by multiplying both sides by my LCD. I could have got one thing over first. So multiply both sides by the cubed root of x. So 2 times the cubed root of x is 2 cubed root of x minus, well, when I distribute it to the 2 over cubed root of x, those cancel, leaving you with just the 2. So minus 2 equals 0 times anything is 0. I add 2 to both sides and then divide by 2. So I have 2 cubed root of x equals 2. So I know the cubed root of x is equal to 1. We can get rid of the cubed root by cubing both sides of our equation. I was just doing this on Math 52 like an hour ago. We get x is equal to 1 cubed, which is 1. So I have 2 numbers that we found to be critical numbers. We have to see that are they in the interval that we were given though? Let me go back and see what interval. We're given between -1 and 3. So 1 is between -1 and 3, and 0 is between -1 and 3. Oops. So critical numbers are x equals 1 and x equals 0. We pretty much just want to plug this back into the original with our inbounds. So -1 was an endpoint. We're going to look at 0, we're going to look at 1, and 3 was an endpoint of our interval. And our original function was y equals 2x minus 3, x to the 2/3. Okay, so if you plug in -1 wherever you see an x, so if I plug in -1 here, I get y is -2. Well, -1 to the 2/3 power. Well, if I take the cubed root of -1, or if I square -1, that's +1. Take the cubed root of that's 1, so that's going to be -3. So this should give me back a y value of -5. If I plug in 0 wherever I see an x, that's going to clear everything out, and that would give me 0. If I plug in +1 wherever I see an x, I get 2 times 1 is 2. Well, 1 to the 2/3 is 1, so I have 2 minus 3, which is -1. So this 3 is going to be the hardest one. 2 times 3, so that's 6, minus 3 all to the 3 raised to the 2/3 power. Which is the same thing as 6 minus 3 cubed root of 3 squared, which is 9. Oops. So about -0.24. So looking at our endpoints and our critical numbers, look at which is the y value that is smallest and which y value is biggest. And so I noticed that the smallest y value that I get is -5. And so -5 is my absolute minimum. And then looking at the largest y value that I get, well, 0 is the largest y value, everything else was negative. And so this is my absolute minimum. I'm sorry, maximum. Let me just kind of move down and see what else I have in here. I'm going to skip because we did some examples. I believe I did like a quotient rule yesterday. So this kind of helps with looking at the concepts. This next example, 6. So it says, so looking at the following statements, we're going to determine if the statement has to be true or is it false? So we want to explain why each statement could be true or false. Okay, so you're given that the derivative of your function at 5 is equal to 0. Do we know then that there is a maximum or a minimum at x equals 0? So does there have to be a max? So notice that here's a function of f of x. Here's an example where if I took the derivative of the function and I looked at the derivative at that function, right? So f prime of 5 in this case is 0, but this is not a max or min value. So here was the case where I was saying, even though we get a critical number, we're getting that it's equal to the derivative is 0, doesn't mean that it's actually a max or a min. And so here's a case where our derivative is 0, but it's not a max or a min. So true or false, if x equals 2 is a critical point, then the derivative at 2 has to equal 0. So remember how we were finding the critical numbers. One way was looking at when the derivative was equal to 0. And so that is one way it could be a critical number, but the other way that it could be a critical number was if it was undefined at that value at the derivative. So f prime of 2 could also be undefined. To be a critical number. So this was false, this was false. So an extrema occurs at every critical point. Well, if we look at the first example I showed you, we had a critical point at 5, but that was not an extrema. That was not a local max or absolute max or absolute min or local min. So if the little m and the big M, or sorry, if little m is the local minimum and big M is the local maximum of a function, then a continuous function, then little m has to be a smaller than big M. So if we had big M here and we had little m here, this is a local max, this is a local min. It's a continuous function. Can you think of any function that you can, kind of look the same. Can you think of any function that you can draw where big M is the maximum, little m is the minimum, and where little m would not be smaller than big M, where it's continuous? So there's no way that you can do that. So that would be, this would be a true statement. Okay. So I wasn't planning on spending a whole day going back over 4.1, but we did do that. And hopefully if you were a little lost yesterday, that kind of clarifies things and you won't have any problems doing the homework. So let me stop sharing my screen.